how to derive that formula. Yeah. All right. So here, look at, we want to find lower bound for comparison-based sorts. Yeah. So from the name, you can see we only consider those sorting algorithms that use comparisons to determine the sorting orders. Yeah. Here you may ask, does that mean there are some sorts not comparison based? Yes. Yeah. There are some sorts not comparison based. Yeah. All right. So here, first I give you the formula. Yeah. The lower bound formula, yeah, I give you before. Yeah. So here, let me give you another time. Log base 2 of n factorial. Yeah. Right. If you do not require comparison based, you can use any method to do the sorting. Then you may have other different sorting algorithms. Yeah. So here, let me give you one special example. Yeah. This semester, we may not have time to cover this one. So this week, the last two next week, last two classes of the semester. So I don't know if so it's very likely I may not have time to talk about that. Yeah. So here, there is another sort. We call a counting sort. This one is not comparison based. Yeah. We do not use any comparison in this sort. You can see the main operation we use, counting. We just count number of elements. Yeah. That operation we do not need to do comparison, right? Do counting. Okay? Yeah. But this is another general purpose sorting algorithm. Comparison based. Yeah. So usually we treat this type of algorithm the general purpose. General purpose algorithm. Okay? But counting sort, not general, special. No. It means there are some special requirements you need to use. Okay? Yeah. So the sorts, you need to assume some special requirements, special conditions. Okay? Yeah. Otherwise, you cannot apply this sorting algorithm. Okay? So what are those special algorithms? First, you must apply on integers. Okay? Yeah. So not floating point numbers, only on integers. Floating point, not floating point numbers. For comparison based, we do not require that, right? So you can see how special it is. Yeah. So you may ask why integers? Because when the elements in an array are integers, then you can do the counting, right? How many elements have value 1, how many value 2, and so on, right? But if floating point numbers, it's hard to do the counting. Yeah, not efficient. Yeah. For example, you have floating point number 1.3578. When you do counting, it could be very messy. Yeah. So in general, you cannot apply the counting operation here. Okay. So that's the first assumption. Second, range assumption. The range cannot be very large. Okay. Range of the values must be relatively small. Okay? Yeah. So this assumption, the main reason we need a second assumption is if the range is relatively large, the performance would be much slower. Okay? So then the counting does not help. If the range is large, we would rather do comparison, right? Yeah. So the reason we want to restrict the range relatively small, because we want to get better performance than the general purpose sorting algorithms. So the range assumption. Okay? Yeah. Yeah. So, all right. So that's the special sort. Yeah. Yeah. But here I only want to talk about comparison-based sorts. Okay. All right. Yeah. So next, let's do some analysis. Why the lower bound is, so here, our goal, I want to show the lower bound. Okay? Yeah. Of the comparison sorts. Is this formula. Okay? And actually this formula is a very good estimate. Very good estimate. Okay? All right, so let me explain how to derive this. Yeah. Because the method is quite useful. The method is called decision tree method. So method we apply here is interesting, useful analysis approximation method called decision tree method. Let me explain this method here. Yeah. Very interesting, very useful. Okay? So what is a decision tree? So here, let's consider a typical comparison. When we look at a comparison, how many different outcomes do we have in general? Okay? Yeah. When you do comparisons, how many different outcomes? Yeah. So comparison between two elements, A and B, right? So one, you have A less than B. One, you have A equals B. And the third one, you have A greater than B, right? It looks like there are three different outcomes. But we want to combine the first two as A less than equal to B, because after this combination, we can get two outcomes. If we just make two outcomes, then we can use binary tree representation. Okay? Yeah. So here, these two outcomes would give us a binary tree representation. Okay? So that would be very convenient. Okay? Yeah, binary tree. So we are familiar with binary tree, right? Yeah. So we like to use simple binary tree to represent comparisons. All the comparisons in the sort. Okay? All right. So now let's look at the typical comparison representation in a binary tree. Okay? All right. So here, let's look at a comparison in a binary tree. Here we use this binary tree to model. I use this word, model the comparisons. Okay, model the comparisons. Yeah. All right. Yeah, let me use comparison between A and B. I use this notation, A colon B. Yes. So this is the node, A colon B. It means we do comparison between A element and the B element. Then we have two different outcomes we need to represent in this binary tree. All right, so one, the left branch node corresponds to A less than or equal to B. Okay, the right branch node equals to A greater than B. Okay, all right, and after that we can do further comparisons. Okay, yeah. Another comparison, and here another comparison. Okay? Yeah. All right. So then, with this basic structure representation, yeah, so we want to use this way. So we can draw a binary tree. So that binary tree we call a decision tree. Okay? So we can draw, because when we do comparison, we just make decisions, right? Yeah. So go where to go. You go to the left branch or right branch. Which decision you make? So we call it decision tree. So draw a decision tree for any sort. We can draw a decision tree for any sort. Okay? All right. Yeah. So next, let me do a simple example to show you, in order to help you understand. How can we draw a decision tree for a sort? Yeah. So let me show you. Then we can do the discussion. Yeah. All right. Here I use a simple example. Okay? Yeah. Example. So what's that example? Sort. A 3-element array. Yeah. So it's a simple example, right? Yeah. Everyone knows how to do it. Yeah. But here, I just give you the idea how people draw a decision tree corresponding to a particular sort. Yeah. Here we represent this array, ABC, these 3 elements. Okay, so we use these ABC elements to draw this decision tree. Yeah. All right, so very simple. Yeah. Yeah. So when we start, we put the root of the binary tree, the decision tree, our first comparison. Yeah. So what's our first comparison? A colon B. A colon B, B, that's our first top root node. Okay? Yeah. Only 2 outcomes, A less than or equal to B, and A greater than B. Yeah. All right. Then the left child node, when A less than or equal to B, what is our next comparison? Here. Okay. Yeah. So although you have several choices, right? But you need to pick one. Yeah. So here I pick B and C. How about that? So my next comparison should be B colon C, right? Yeah. So then two possible outcomes, B less than equal to C and B greater than C. Yeah. Okay? Yeah. But when B less than or equal to C, we get this array sorted. Because we know the explicit order after these two comparisons, right? So now our node won't be any comparison node. Our node must be the outcome node. Okay? Sorting result node. Yeah. So we use a rectangular box to represent the sorting result. A less than or equal to B less than or equal to C. Yeah. So that's the bottom leaf node. We reached the bottom. It's a leaf node. Okay, sorting result. Yeah. All right, but here, this side, B greater than C, it's not enough to get the array sorted. We need one more comparison. That comparison must be between A and C. Yeah. So we need to do a comparison A colon C. Okay, all right. So then left branch A less than or equal to C and the right branch A greater than C. Okay. Now we can write the sorting result nodes, rectangular box node. Yeah. All right. So this one, sorting result, okay, A less than equal to C, strictly less than B, right? Yeah. And here, C is the smallest, C less than A, less than B, right? Yeah. Or less than or equal to B. Yeah. To write it more accurately. All right, yeah. But this is one side of the sorting results. Three possible sorting nodes, right? The other side, this side, right branch, similar. Okay? Yeah. Yeah. You know, you use the same way you can produce the right subtree. Yeah, right subtree. Yeah. So similar. Okay? So here I do not, draw it. Yeah. Similar structure to save some space. Yeah. Yeah, because I need, quite some space to discuss our next step, derive the lower bound. Yeah. All right. So now, after this simple example, you can understand how people draw a decision tree for any given comparison-based sort, yeah, in the straightforward way. Yeah. All right, so now we need to do the same thing. This time, we do this on that general, abstract, sorting n-element array. So this time, okay, all right. So the general problem, okay, sort an n-element array. All right, so that problem, okay, all right. And this time, now, we have to explore some properties. Because if you try to draw decision tree, so only partially, it won't be easy. Yeah. So we have to, discover some main properties of its decision tree here. Yeah. All right. So let's look at it this way. All right. First, we know for any such sort. Yeah. So here we're talking about any comparison-based sort that can solve this problem. Okay? Yeah. So there is a decision tree for it. So we just discuss the common properties for a typical such sort. All right. So there is a root node. Okay. Many comparisons. Okay, going down. Yeah. Certain level. Some sorting outcomes. And so on. Okay. All right. So some quite general structure. Yeah. Yeah. All right. Now our discussion here. Yeah. The first discussion. First, we need to estimate. Okay. How many leaves? Estimate how many leaves in the decision tree. Okay? Yeah. So how many different sorting results? How many different sorting results? Can you imagine that? Yeah. Because given n elements, so you can imagine x1, x2, and so on. Okay? xn, and so on. All right? Each sorting order corresponds to a permutation of these n elements, right? So you know the permutation concept, right? So each sorting result corresponds to a permutation. Yeah, so the permutation concept from your discrete math. Okay? All right. So how many permutations do you have with n different elements? Here we assume these n elements are distinct values. Yeah. So the answer is n factorial. Okay? All right. So that means here estimated how many leaves, the answer is greater or equal to n factorial. Greater or equal to. Yeah. So you may ask me why greater or equal to, not exactly equal to n factorial. Because remember here we are talking about a general algorithm, right? Yeah. So here we're talking about a general comparison-based sorting algorithm. A general sorting algorithm means any algorithm you just get n element array sorted, right? Yeah. If an element that can get n element array sorted, it's not necessarily optimal, right? Yeah. It could be optimal and it could be non-optimal, right? Yeah. If it's not optimal, that means this algorithm may do some redundant work. This algorithm may do redundant work, redundant comparison, redundant comparisons. That's possible, right? Yeah. Redundant comparisons, okay? Yeah. So if it's redundant comparisons, then when you count the number of leaves, some of the sorting result could appear more than once. Yeah, but yeah, because redundant. So redundant more than once. Yeah. So if you have redundancy, then the number of leaves would be greater than n factorial. Okay? Yeah. Only when you do not have the redundancy. Okay? Only when you do not have the redundancy, then the number of leaves equals n factorial. Okay. So here, so we should use this greater or equal to sign. Yeah. So that's one. The next one. Next important property we observe. So that is the worst case. Yeah. Because when we estimate the lower bound, we should look at the worst case efficiency, right? So when we look at the worst case efficiency, okay, worst case efficiency, it corresponds to, yeah? How do you represent worst case efficiency in the decision tree? In the decision tree, corresponds to the height. Binary tree has a height, right? Corresponds to the height. The height. The tree has a height. Okay? Height. So here we use h to represent that. The tree height. So here it's the tree height. Okay? Yeah. It's not the node height. Yeah. In our heap sort discussion, we look at the height of a node. Here, the concept here is height of a tree. So that's different. Height of a tree, we use height of the root node for the height of the tree. So this height means height of the tree. Height of the tree, okay? Yeah. Yeah. Not height of one particular node. In our heap sort, we consider height of a node inside the heap. Yeah. So try to separate the concepts. So here, height of the whole tree, so we look at from the root, okay? So our starting point is at the root. Then we want to find a path, follow a path, reach the bottom, reach a leaf node, and that path must be the longest path. We want to find a longest path. We know some paths are shorter, some paths are longer, but we consider the longest path. How do you define longest? We count the number of edges. Edge 1, so we count 1. Edge 2, we count 2. When you move along a path down, you count how many edges do you have. That number we use to measure the height. Okay, the number of edges. So here, for example, let's look at the length of this path. 1 edge, 2 edge, 3 edge. So this path has length. Yeah, so I use length. Length equals 3. Okay? This one 1 edge, 2 edge, we reach the leaf node. So this length equals 2. Okay? Yeah. But when we use the height, we use the longest one. We use the 3. We do not use 2. Okay? Yeah. So that's the height. Now, the worst case efficiency corresponds the height of the tree. Okay? All right. Yeah. So another representation. Yeah. Next one, we want to estimate the relationship between, so here, L, we use L to represent number of leaves. Okay? Of leaves. Okay? L. Okay? Capital L. Yeah. The number of leaves. And we know, based on our analysis above, we know L greater or equal to n factorial. Okay? Due to redundancy. Okay? The nodes, redundant nodes. Okay? All right. Yeah. All right, so now what's the relationship between capital L and H? What's the relationship? So we compare with, we want to find a relationship between L and H. Okay, so what's that relationship between capital L and capital H? Yeah. All right, so here we need to do imagination. Yeah, so to get this relationship, we need to do some imagination here. Okay. Yeah. So what kind of imagination? Yeah. All right. So think about, given the height of a decision tree. Yeah. So first we fix height h. Yeah. So we fix. When you do consideration, we fix that height h. Okay. So you draw a binary tree with height h. Yeah. So you fix it. Okay. All right. Then you consider, because with the same height h, you can get many different binary trees, right? Yeah, you have many different ways to draw a binary tree with the same height h. Okay, all right. Now you think about which binary tree with height h gives you the largest number leaf nodes. Can you answer this question? Yeah. So you have so many different binary trees with the same height. Which one would give you the largest number of leaf nodes? Okay? Imagine. Can you, in your mind, can you envision a picture? So the binary tree with the maximum number of leaf nodes. Okay? Yeah. So you try to expand. You try to expand your branches to cover as many ground as, as many leaf nodes as possible. Okay? Yeah. Cover the ground, the tree. Okay? Upside down. So that tree you want to cover, as much ground as possible. Right? Yeah. So imagine that. Okay? Yeah. So the answer is complete binary tree. Okay? So when you get because the complete binary tree, you only have one case for the complete binary tree, right? So let's use the complete binary tree. Okay? Yeah. When you get a complete binary tree, you have the maximum number of leaf nodes. But for a given height h with complete, a complete binary tree with height h, how many leaf nodes? How many leaf nodes? 2 to the n. Yeah, so it's a power of 2. Yeah, first the power of 2. Yeah. Power of 2. Yeah, so if you count from root, because the root, at the root, if the root already touched the ground, if the root is a leaf, if the root is a leaf, then you have 1, 2 to the 0, right? Yeah, 2 to the 0. Then you have one more level, 2 to the first. Another level, 2 to the second. 2 to the second, height equals 2, and so on. Okay? So 2 to the h, when the height equals h, the number of leaves 2 to the h. Okay? Yeah, but that is for the maximum number of leaf nodes, right? Yeah, maximum number that should be greater or equal to the general L, right? Yeah, because the L number, capital L, is the general number, not necessarily the maximum. Okay? Yeah. So that's the L. So 2 to the h should be greater or equal to L, and another inequality we derived before, n factorial. Okay, now let's skip this L part, so we get 2 to the h greater or equal to n factorial, right? Yep. All right. Yeah, n factorial. All right. Then we take log base 2 both sides. After that, we take log base 2 both sides. Yeah, let me use space here. So we get h greater or equal to log base 2 n factorial, right? Yeah. H integer, log base 2 n factorial may not be integer, but we want to make this greater or equal to sign always true. Can we assume h should be greater or equal to the ceiling function of log base 2 of n factorial? Not floor function, ceiling function. Yeah. Floor function, so you may not cover, sometimes you may not cover. Okay? Yeah. So when you use the ceiling function, then it's always true, right? If h greater or equal to the ceiling function of log base 2 of n factorial, then thus you guarantee this inequality always true. Yeah. If you use the floor function, you cannot guarantee the bottom inequality always true, right? So for that reason, our best estimate for the worst case, here we estimate the worst case, is the ceiling function of log base 2 n factorial. How about that? Okay? So that's the whole derivation process. Okay? Yeah. The lower bound formula for comparison-based algorithm. Okay? Yeah. So try to understand. Yeah. Here I use this example. I want to teach you how to use the decision tree method to do analysis. Yeah. So in some special situations, it is very useful. Okay. All right. So let me finish this topic.